Sometimes a subatomic particle will overcome a barrier that shouldn't be possible to overcome, and they do it with quantum tunneling. But what's quantum tunneling? Well, to understand quantum tunneling, you've got to understand probability waves.
In the early 20th century, everyone thought light was a wave, and only that.
But light behaved in certain experiments as if it were a particle.
For example, the photoelectric experiments showed that when the right frequency light was shined into metal, it knocked electrons off the metal in a way that could not be understood using wave mechanics, suggesting a particle collision. While other experiments, such as the double-slit experiment, showed that when light was shined through two slits, it would act as overlapping and combining waves.
In order to explain these contradictions, Erwin Schrödinger and Max Born came up with probability waves. To explain this simply, a quantum particle usually exists in an infinite amount of
places, velocities, and energies at the same time, but this is not always so. Sometimes a phenomenon called wave function collapse occurs, which is usually triggered by interaction with some other forces. When wave function collapse occurs, the particle has a single location, energy, and velocity. I'll focus on location. The probability of finding the particle at a certain location when wave function collapse occurs can be graphed as a wave. The highest and lowest points of the wave represent a higher chance of finding the particle there, and vice versa. Additionally, as time passes, the wave moves and acts like a normal wave, hence the name probability wave.
This theory was revolutionary. It fit into all the experiments perfectly.
Probability waves can overlap and combine just like the waves in the double-slit experiment. And if both their wave functions collapse, a photon can hit an electron.
Additionally, probability waves can be accurately graphed and predicted using some, complex math. Since then, lots of evidence has been collected proving the existence of probability waves. But how does this relate to quantum tunneling? Well, it's actually pretty simple. What happens when a probability wave hits a barrier?
It does what any other wave would do. It bounces off, but not completely. Some of the wave actually goes into and through the barrier. The part of the probability wave residing past the barrier represents a small but finite probability that when the wave function collapses, the particle could be on the other side. So now you know how quantum tunneling works. Just don't try it at home.
You may be wondering how this is relevant to humans. Actually, quantum tunneling is necessary for life.
Quantum tunneling enables particle probability waves in the sun to overlap just a little despite repulsive forces that would otherwise keep the particles apart. This allows the particles a chance to fuse once wave function collapse occurs and enter a more stable state, causing a release of excess energy. That released energy from nuclear fusion sustains life on Earth.